Hello Internet, my name is Quinn and this is Blondihacks. I'm working on my locomotive this week and I'm going to get started on the expansion links. These sound like one component, but they're actually an assembly, a complex assembly made up of 800,000 parts, and we're going to get started on that right now. The expansion link is a curved slotted linkage that is suspended in space around the radius rod. It's mounted on a bracket from the motion bracket called the link bracket. It's this curved slotted feature that you see here in pink. If you watched my wall shirts video, then you know that this linkage allows the engineer to control the travel of the valve by reducing the throw of the return crank as it is applied to the valve itself. This behaves very much like the transmission in your car, allowing the locomotive to switch between slower, higher power operation or higher speed, more efficient operation. This linkage is also what allows the locomotive to go in reverse, so very much the brains of the entire operation. Now it looks like a single linkage, but it's actually a sandwich of multiple components. I'm going to start with the meaty center of that sandwich, the expansion link itself, and like everything on this channel, it starts on the bandsaw. I've got some 1018 flat bar that I'm going to be using for this. I don't love using 1018, but it's what I could get in the dimensions that I wanted for these parts. This is cold rolled material, and we're going to be making some very thin parts out of it, so I'm going to normalize it first to prevent it from warping as a result of the machining work. If you've ever wondered what cold rolled steel actually is, they take normal hot rolled steel out of the mill and they run it through the dies again, this time cold. That removes the mill scale, gives the material a nice finish, and allows them to hit a much tighter tolerance dimension, giving material that's much nicer to work with in machining. However, running the material through the dies again cold puts a lot of internal stresses into the material, which is what creates the warpage that we're trying to prevent. So normalizing, heating it to cherry red, and letting it cool down nice and slowly releases all those internal stresses. Shh, the steel is sleeping. All normalized and cooled down, now I'm going to start machining these by putting a reference edge on both pieces. The two expansion links are identical, so I can make them at the same time. Even though they are left and right-handed on the locomotive, they are actually symmetrical on their vertical axis, so you can make them both identical and flip one side to side to put it on the other side of the locomotive. Once I've got the edges machined, then I'm going to thin them down on their large face. The material is a bit thicker than the final links need to be, so I thin it down, machining both sides, and this is where they would warp if I hadn't normalized them. Since the links are identical, I'm going to take these two pieces and glue them together and do all of the machining together. I've drilled some holes in them for fixturing, which you'll see in a second, and I'm going to use those holes to keep things in alignment while the super glue sets. I clamp those up for a good 20 minutes to make sure that glue is nice and strong. And of course I've prepped the surfaces, degreased and cleaned and so on thoroughly. The strength of super glue is very much a function of how well you prep the surface beforehand. Now I can bolt these two blanks to the fixture, which you may recognize from the video on the link blocks. I intentionally, for once in my life, thought ahead a little bit and made it large enough to do these expansion links as well. The holes are off-center so that they will clear that area of the fixture block that I did not hit with the fly cutter because I'm dumb. Didn't leave myself enough room there. To get ready for these parts, I did a whole bunch of work in CAD. I spent a good couple of hours drawing up these parts in 2D and having CAD tell me what all of the angles of all of these different cuts and things are going to be. These are really complex parts, but if we know all the numbers, we can actually make them in a fairly straightforward way here on the rotary table. However, there's a lot of math to figure out what all the angles need to be. Once I'd done all that math, I realized the parts will not fit on my blanks the way I had drilled those fixturing holes. So I had to slot out the holes, resurface my fixture plate, giving myself more space so that I could center the blanks on the fixturing holes. Yeah, well, we're working this out as we go. Then I did a little dry run going through all the numbers on my CAD drawing with an end mill mocked up, just to make sure that A, the parts were going to fit entirely within the blanks, and B, that my math looked like it was sort of sensibly, vaguely correct for how I think things are going to go on these parts. I'm also double checking all my math in real time, and I'm calculating all of the decimal degrees that CAD gives you into these degrees, minutes, and seconds that the rotary table requires. But after checking and rechecking everything 700 times, I decided sooner or later I'm going to have to start cutting something and just see how it goes. So, well, here we go. I'm going to start with the easy ones, which are the holes that hold all three layers of the sandwich together. These are simple clearance holes at the tops and bottoms of the link. These are Simple except for the fact that, of course, everything is on an arc here. So the x-axis of my part is the rotary angle of the table. Now, the rotary table, of course, does not have a DRO on it, so I do have to manage backlash. That's very important. So every time I do a lateral move on this setup, I'm always going from right to left on the part, which is low degrees to high degrees on my rotary table. And anytime I have to go back the other way, I always have to remember to come all the way out and go back again to make sure I'm not in backlash. If you don't have DROs in your machine, this is automatic muscle memory, I'm sure, but for us spoiled whippersnappers who've never not had a DRO, on the milling machine at least, then it takes some thinking to make sure that we're respecting the backlash of the setup. And especially with this long extension on the rotary table, there's actually quite a lot of backlash. Any error or movement in the table is very much exaggerated because we're working so far from the center of the table. This third hole is the little dog leg at the bottom of the expansion link that actually attaches to the return crank. That gets reamed 2mm like most of the pins in the valve gear do. And now in with the milling cutter, and we can start cutting the $1,000,000 feature of this part, which is the curved square slot that the link block actually runs in. I have a center cutting end mill, so I'm plunging down a little bit at a time and making light cuts. I have a pretty long way to go down through both parts, so rather than having to try and worry about removing backlash on every single pass, what I'm actually doing is making this cut narrower than the final cut needs to be by a good 1/2 degree on the rotary table, so that I can mill back and forth with reckless abandon, not worrying about backlash, and then I'll do my final cuts with backlash in mind so that I end up on the right places with the ends of the slots. This end mill is also narrower than the final slot, so what I'm doing is roughing in the center of the slot effectively, all the way down through both expansion links. This operation, of course, is going to leave a round-ended slot, and we need square ends on our curved slot, as per the drawing in the corner, but we'll be squaring up those corners later in a different operation. Then for the final cut, I come up out of the part, move all the way to the right, well outside the backlash of the table, come back into the left to the final correct starting position for the slot, and then I plunge straight down with my end mill, so this end of the slot will be right on where it's supposed to be on the angle measurement, and then I feed all the way across, basically doing no work at this point because all that material's already been removed, but then I move all the way past the end of the roughed in slot to get the exact correct finishing angle. So again, the dimensions of the slot will be correct because all of the backlash has been removed, and I just saved myself some time by roughing in the middle. Now I need to widen it out by the difference between the final dimension of the slot and the width of this end mill, so I'm pushing the work away from me a little bit and cutting the side of the slot that's nearest to me first, widening that out a little bit. And that's not an accident, that's important because by cutting the near side first, it means that I'm conventional milling and not climb cutting. Now you can often get away with climb cutting, especially with light cuts. You've seen me do it all the time, probably without my even thinking about it. However, with a setup like this, you absolutely cannot climb cut because that cutter is so far from the center of the rotary table. The cutter has a lot of leverage on the rotary table, and boy oh boy will you feel the cutter trying to rip the backlash out of that table as you're cutting if it's climb milling. And I know this because I tried that first, because I tend to cut the back of the slot first just out of force of habit when I widen slots like this. And boy was the rotary table unhappy about that. Honestly, even when conventional milling, you tend to get a little bit of rattling out of the rotary table when you've got this much leverage on it. After that initial widening, I test with the link block. I didn't really expect it to fit yet because I always tend to cheat a little bit under size on a critical dimension like this just to make sure that I don't overshoot it and then massage it out from here. And sure enough, that doesn't quite go in. The gauge pin tells me that I'm 2 thou under, so that's a nice place to be. I'd certainly rather be here than 2 thou over. The fit of this link block is really critical, so it's worth taking my time and massaging this to a perfect fit. Skip ahead a few minutes in time now, and I've done 2 more very light cuts on each side of that slot. And here's my nominal size gauge pin, and that is a really nice sliding fit in there. It's probably a few tenths over, but that's okay. This piece does need to move, so that's a good thing. Let's see how the gauge block itself fits in there. Oh, very nice. Does it move? Oh, look at that. You really couldn't ask for a better fit than that. There's a perfect sliding fit with 0 play. I was nervous about this cut because this slot dimension right here is the whole ball game. This whole assembly is worthless if that isn't perfect, and well, there may have been some celebrating after that. It's a better fit than I even hoped to get, honestly. The rest of these cuts are comparatively easy because after this point it's all aesthetic. We're just creating the nice looking outlines of the parts. The functional stuff's all done. However, there is a lot of this work to do. So I start by carving out the underside of each of these. I guess it's the forward edge of the expansion links. This cut is much longer than the part itself. It was just easier this way to be able to start and finish outside of the material. That's a much easier cut than having to plunge anywhere along the way. I had no such luxury for the opposite side of the part, however, because that cut I do have to plunge at one end because I can't start outside the material without hitting my fixturing bolt. And the other end of this cut actually has to stop in an exact place because it becomes the fillet between the body of the expansion link and the little dogleg linkage at the bottom of it. I've done what I can on the expansion link, but now I need to pause and work on the trunnion plates which go on either side of this piece. So I need to remove this piece from the fixture. However, I need to be able to get it back into this position later. So I'm going to drill and ream some alignment pins that actually are going to be useful for the trunnion plates as well. The 6 plates that make up these 2 expansion link assemblies have a ton of features in common, so I can save myself hours of setup time by putting these little pins in there and making this fixture repeatable. For this sort of thing, I keep drill rod around. I simply hacksawed some chunks of this, chamfered the ends with a file, and voila, we've got perfect alignment dowels for a fixture like this. Drill rod is such useful stuff to keep around. Now I can slide these pieces off here knowing that I can get them back into this exact position at any time. On to the trunnion plates. For this I prepared 4 blanks, well actually 5 new blanks of this same material. These have again been normalized. And these pieces are thicker. They're actually the same nominal dimension as this material. So I prepared 5 blanks to make sure that I'd get at least 4 that were straight. Normalizing doesn't actually prevent warping. It's more like a pre-warping. You normalize before you're going to machine, but if you're not going to machine the outsides of the dimensions more than any warping might cause, then the normalizing can actually scrap the part. You still have to do it, so that's why I do an extra one and take the 4 that are straight. And in this case, one of them was indeed warped, so I'm glad I did that. These 4 blanks then get the fixturing holes and the alignment dowel holes put in them. It doesn't matter where on the blanks these holes are, as long as there's enough room within the material to get the parts out of them, and as long as the holes are the right distance relative to each other. Because of course the outsides of these blanks are all going to go away in the final parts, just like for the expansion links. Now I can start cycling these parts through the fixture to add the features to them, and I don't have to change anything in my setup. My DRO is already configured for the right angles and positions and so on for all of this stuff, because it's all the same as the expansion link was. So again, I start by doing the lower cut that forms the forward edge of the trunnion plate, exactly the same as the expansion link. The alignment dowels are actually extra tall because I had considered doing all of these parts in one setup, stacking them all up. But it turns out for these side milling cuts, it actually doesn't save you any time because you have to take multiple light cuts anyway, and you end up doing really deep slot cuts, which are slower and more difficult to manage chips and so on. So doing them one at a time just made more sense. It's very quick to cycle the parts through this fixture, and I had a lot of these cuts to do, so top and bottom edges of all 4 trunnion plates, just had to take my time and settle in and, well, get it done. Once I have all 4 plates brought to this point, I've got the top and bottom edges defined. Now I can start putting holes in them, and for this I can stack them up. I can do them 2 at a time because the 2 outside trunnion plates both have a clearance hole in them where the bolt that fixtures the sandwich together goes through. So I might as well do these at the same time because of course then I only have to do 1 drill for each hole. Of course, just like on the expansion link, I'm always being mindful of my backlash when I'm doing these kinds of lateral features. I'm always making sure to go from right to left, which is again low to high on the angles on the rotary table, and always making sure to start well outside the backlash and moving across. And of course, a little extra brain power required because we're not doing this in degrees, we're doing this in degrees, minutes, and seconds on the rotary table vernier scale. Now, to be fair, I only did this 2 minutes precision, not 2 seconds, so I didn't actually have to use the vernier on that scale. I only had to use the subdivisions on the hand wheel, which are 2 minutes per tick. And 2 digits of minutes accuracy is 1/10 of a degree decimal accuracy, so that's just fine for this. Now for the other 2 pieces, they get tap drilled and tapped because they are for the other side, the insides of the trunnion plate assembly, where the bolts thread into to hold it all together. So I drilled and tapped these all the way through as a pair as well. And then I go back to the outside trunnion plates to do these one at a time because the tops or outsides of these both get countersunk for the screw heads. As is my usual method, I've got my shop-made D-bit countersinking bit, and I just go a little bit at a time until that sits flush or just a hair below flush ideally. And then I've got my depth established on the quill DRO, and I do the rest of them to that same depth. Now the next set of cuts is very tricky. On the backs of each of the trunnion plates, we need to make a recess where the radius rod passes through, but the ends of that recess have a tricky series of 4 angles on them, 17 degrees on one side and 31 on the other. Those angles are clearance for the radius rod at the full travel of the expansion link. Because they are just clearances for a moving linkage, they don't have to be to the 1,000th accurate, but we still do need to make them reasonably accurate. So I started out by trying to lay this out on the surface plate. Using the pin in the center hole as a reference, I tried to lay out the distance from the hole where the apex of those 2 angles comes together. However, I quickly realized this was a fool's errand because what I really need is the radius of the clearance all the way around that hole. Because each of the 2 angles that we need to cut meet the radius of the clearance around that hole at some difficult to calculate place, and I don't know where that tangent point is. Now I could again go back to CAD or get out the calculator and start doing the math to try and calculate that. However, instead what I did is turned up a little button that fits into each of the holes and has the correct clearance radius around that hole, and I traced those circles onto the pieces. So now I can just make my angle cuts up until they touch those circles, and the tangent is going to land in the right place because it's going to be somewhere on that circle. I don't need to know where on the circle it is. I just need to move closer and closer until it touches that circle somewhere. And again, cutting to a layout line is sufficiently accurate here because these are just clearances. Getting the actual angles themselves accurate is easy because conveniently the drawings use the center line of the part along the short axis as the reference for those angles, which is the same axis that my setup is using on the rotary table. So I literally just had to set the rotary table to 17 degrees for this first cut and 31 for the other cut. I went all the way down to depth in a series of fairly light cuts, well clear of that scribed circle that we just made, and then using some good light and magnification, I moved the cutter over a little bit at a time, just a few thousandths at a time, and side milled my way over to that layout line. Now I only have to do that once because once I've got that X position set on the DRO for this first 17 degree cut, then I can pull this part out and cycle the other 3 through, and I can make this same cut to the same way. Then I go 17 degrees the other way on the table and I make the same inside cut on the other end of all 4 parts. Again, on the first one I have to do that empirical determination of the X value on the DRO, but then I can cycle through the other 3 very quickly. Then I set the rotary table to 31 degrees and I do the same cut on the back side of each part using the same process. And the nice thing is the depth of all of these cuts is the same, so because the parts are repeating in X and Y, and of course they're all the same thickness, the whole setup repeats in Z, so I never have to change my quill DRO, and I'm always going to be cutting to the correct depth. Then that whole middle section needs to be removed, so for this I switched to a nice big cutter so I can do this in a series of single passes. I did have to do a new touch off for this because it's of course a different cutter, and from one end mill to the next it doesn't repeat on Z unless you've got some sort of tool holding system like the Tormach TTS, but for me I just make light cuts down until the surface matches the 2 surfaces that were created by the angle cuts, and then again once I've established this for the first part, it's very quick then to cycle the other 3 through. And of course the tool marks will look different cutters, different setup, etc. But as long as you can't feel any transition there, then the surfaces are coplanar and that's all that matters. You can see how those 4 angle cuts now have revealed the recess that we needed on the undersides of the trunnion plates. However, that is all the time I have this week. We are going to have to leave these parts here and come back to them next time. These are really complex parts, and I'm really enjoying making them. I hope you're enjoying watching the process. Thank you so much for watching. Thanks to my patrons for making all this happen, and I will see you next time.